All right, so this final video on equilibrium applications is going to involve determining whether precipitation is going to take place. And we're going to kind of take it back to what we did when we first got into equilibrium and compare Q to K to determine whether a precipitate forms or not. If we are going to have a precipitate, we need our Q to be greater than our K value because we'll have a supersaturated solution and we would have to shift back towards the reactants forming solid until we reach equilibrium. If we aren't going to have a precipitate form, we want our Q to be less than our K value, meaning more ions are going to need to dissociate from the solid before we're able to reach equilibrium. And when we have a saturated solution, we are right on the edge. Our Q would be equal to our KSP value. You would not have a precipitate, but you would also not have any more ions dissociate into solution. One thing that I do want to make sure I point out with this, it says you have to figure out the initial concentrations to know whether Q compares to your KSP. If you're given the concentrations, it's pretty straightforward. But if you're mixing two different solutions together, we've done this before in a few labs, we have to account for the dilution factor that will take place when those two solutions mix. So determining the initial concentration will involve using our dilution equation. So we've got four examples to work through. The first one, we've got silver chloride that was put into a beaker, and we're told what the concentrations were of silver and chlorine in the beaker. And we want to know, is this reaction or is this solution at equilibrium? Is our Q equal to our KSP? So to determine what our Q is and to be able to compare it to our KSP, we need to know what the KSP expression will look like for this particular solid. Arrows are fixed this time. Silver chloride is dissociating into silver and chlorine ions, so the KSP expression would be the concentration of silver and the concentration of chlorine ions multiplied together. We know what their respective concentrations are, 1.2 times 10 to the negative fifth. So those both get substituted in for silver and chlorine. And when we calculate this, we get that Q is 1.4 times 10 to the negative 10th. That is smaller than our KSP value, so we have not reached equilibrium. We have an unsaturated solution. We would need additional ions before precipitation would take place, or for us to even reach saturation. In our second example, I'm giving you one of the two ions and asking you to tell me what the concentration would need to be of the remaining ion if we're going to have precipitation occur. We've got a solution of 0.010 molar barium ions, and we want to know the concentration of the sulfate ions. We're told that the solid that we're trying to form, the precipitate, is barium sulfate, and we're given the KSP of barium sulfate is 1.1 to the times 10 to the negative 10th. So let's write our equation showing the dissociation of barium sulfate into barium and sulfate ions. And then our KSP expression would be one barium and one sulfate ion, since they're all in a 1-to-1 ratio, being multiplied together. We know the KSP value and we know the barium value. So it says we need Q to equal KSP for the precipitate to bend. Basically, we need Q to be just over that KSP value. I should have did Q equal to KSP is when you're at saturation. Anything above that would cause a precipitate to form. So to figure out what sulfate's concentration would be, we would take the KSP value we were given and the concentration of barium and solve for sulfate, which we got to be 1.1 times 10 to the negative 8th. So anything greater than 1.1 times 10 to the negative 8th would be needed of sulfate for that precipitate to form. There's a correction that I made on this problem. I believe yours says that barium is at 2 times 10 to the negative fourth molar. Please note I used 2 times 10 to the negative third just to make the numbers a little bit more realistic. You'll see why. We have a solution that's got both barium and calcium mixed in it. And we're told that hydroxide ions are being added to the solution. And we want to know which of those two precipitates, the barium hydroxide or the calcium hydroxide, will precipitate out of solution first. And to do that, we're going to need to figure out how much hydroxide we would need for each of those two solids for precipitation to occur. So with that in mind, we're going to write out two dissolution reactions for barium hydroxide and calcium hydroxide respectively, and two KSP expressions. We're going to take one of them at a time. So there's barium hydroxide. Its KSP would be barium times hydroxide, but the hydroxide would need to be squared. So Ba2 plus times OH minus squared. We know the barium concentration and we know the KSP of the barium hydroxide, so we can substitute those two values in. Hydroxide is going to increase by a factor of 2x normally if we were dissolving it, but remember we're adding the hydroxide to it, so we just need to know what the concentration is of the hydroxide that we're adding. So when we solve this through to get what the concentration of hydroxide would need to be just above, we get that it would be 1.6 molar. And that's pretty large. So my guess is this is probably not going to be the one that's going to precipitate out first, but we'll take a look at calcium just to see. The calcium hydroxide equation is going to look a lot like the barium hydroxide equation since they're both in the same group, and the KSP expressions are going to look very similar as well. We have the KSP value for calcium hydroxide, 5.5 times 10 to the negative fifth, and we have the calcium concentration, 4.0 times 10 to the negative fourth. When we go through and do the math, we get that the hydroxide concentration needed to allow calcium hydroxide to precipitate out would be just above 0.37 molar. That being much smaller than the hydroxide that you would need to precipitate the barium hydroxide means that calcium hydroxide would precipitate before the barium. And then our final example is one where we have to account for the dissolution. We have to account for the fact that we're mixing two solutions together, and so we're going to have a dilution of their volumes. We have 50 mils of 0.1 molar lead-2 nitrate with 50 mils of 0.1 molar potassium chloride, and we want to know for precipitate forms. When we're given the KSP of lead-2 chloride is 1.6 times 10 to the negative fifth. Why did I not give you another KSP? Well, you've got the other two ions are potassium and nitrate, and those are both soluble, so they are not going to form any sort of precipitate. So the equation that we need to focus on is the one that would result in the lead-2 chloride being formed, and that would form after we have sufficient concentrations of the lead ions and the chloride ions. And we need to know what those concentrations are so we can compare the concentrations we have of those two ions to the KSP value to determine if a precipitate indeed forms. Again, because we're mixing these two solutions together, the concentration of lead and the concentration of chlorine are not going to remain 0.1 molar. We have to account for the fact that they're being diluted. We had 50 mils of each, so we now have a volume that's twice the size of what we started with. There's your KSP expression for the lead-2 chloride. So we're going to use M1V1 equals M2V2 to determine what the new concentration will be for lead. It's going to be half of what we started with, 0.050 molar. Since the volume doubled, the concentration decreased by a factor of 1/2. And the same thing with chlorine. Again, we only had one lead in the lead-2 nitrate, so that's why the concentration initially was still 0.1, and the same thing with chloride. But because the volume doubled, the concentration was decreased. We now know what the concentration of lead and chlorine is when the two were mixed together. And if we substitute those into our KSP expression to solve for Q, we get that our Q is 1.3 times 10 to the negative fourth. That Q is substantially larger than our KSP by a factor of 10, so therefore our precipitate did form. As long as our Q is greater than our K, we do have precipitation take place. And that's the end of this particular video.